My name is Aloisio Dourado, and I will present our paper Data Augmented 3D Semantic Scene Completion with 2D Segmentation Priors. Semantic Scene Completion is a recent computer vision task introduced in 2017 by a research group from Princeton University. The input for the task is a RGBD image captured by a structured light sensor like Intel RealSense or Microsoft Kinect. The goal of semantic scene completion is to classify every voxel of the scene with a semantic label indicating the class from which they belong, including occluded voxels. Very early solutions rely only on the depth map to perform the task. The next set of solutions started to explore more modes of the input image, projecting 2D features to 3D and fusing them to the visible surface volume in a Bimodal network. After that, most solutions started to explore 2D segmentation networks to extract features from the RGB image and then project to 3D to further perform fusion. More recent works started to explore other modes of the input. EdgeNet, for instance, applied Canny edge detector to the RGB image and projected the edges to 3D before fusion. A posterior work combined the edges from EdgeNet and the 2D feature projection from TNetFuse with excellent results. All work so far uses what we call a straightforward pipeline. In a straightforward pipeline, training and inference occurs in a single direction with no loops. Very recently, the current state-of-the-art for this task was achieved by a solution that uses iterative completion, instance completion pipeline to fuse depth map and projected 2D features. However, this kind of solution tends to be more time and resource consuming due to its iterative nature. As the 2D segmentation network, we use a bimodal solution that combines RGB and surface normals as inputs. Unlike most of the previous solutions, which project 2D network inner features, we used the output probabilities of the network through a softmax function. To deal with memory constraints, we projected the 2D priors to 3D in low resolution. The projection is made from the depth map. To the 3D volume, we add an extra channel to the empty class, so for each voxel we have 12 channels of priors. Spawn fuses the fine-grained structured features from the depth map to the coarse-grained semantic guidance from the surface priors, generating the final result. The building block of Spawn is a modified DDR block with batch normalization and specific points. We are also the first to use data augmentation applied to semantic scene completion. Our 3D data augmentation approach is applied directly to the inner 3D volumes of the network and is based on 3 fast and simple transformations. Our paper includes a detailed evaluation of our contributions in a comprehensive ablation study. Here we compare our results to previous iterative and straightforward solutions on SunCG synthetic dataset. Here we compare our results on NYU DV2 real dataset in 2 training scenarios, with and without fine-tuning from SunCG. On NYU CAD, which presents real scenes with synthetic depth maps, we reached the best results in all scenarios amongst all pipeline types. Qualitative analysis shows that the results are much superior than the baseline model, with accuracy close to perfection. To conclude, we summarize our contributions. Spawn, a new network architecture that exploits prior probabilities from a 2D network. BNDDR, a new building block with more discrimination power than its predecessors. A data augmentation approach that reduces overfitting. Our solution surpassed all previous works of similar computational complexity, and the boost on NYU CAD was 11.8%. Thank you.